It's modeling the recoil and spin from a black hole binary merger.
Thanks. So first of all, I'd like to thank the organizers, not so much for having invited me, probably that's not something that I should thank them, but for having the stamina to continue this. I think it's a very important meeting point for people of different communities to come and talk about binary black holes. Alright, so the title of my talk is Modeling the Recoil and Spin from Binary Black Holes, and I'll try to teach you all I know, which isn't too much, about this topic. I'll give you first of all the answer as we know it and as it appears mathematically in terms of the kick and of the final spin. And then I'll try to guide you through how we reach this understanding. And I'll really go through the historical steps that have been taken in order to reach these final answers. And I will start from equal mass and equal spins aligned binaries, and equal mass and equal spin aligned binaries, and equal mass and equal spin aligned binaries, and then generic binaries. Just to make sure that I use a terminology that you understand. To me, aligned means aligned with respect to the orbital angular momentum. So that's my reference vector. Anything which is parallel to that vector is aligned. Then I can have configurations which are parallel or anti-parallel with respect to each other. Okay, so aligned are like this, and of course these are parallel, but they also are parallel and they are also anti-parallel. Okay, I won't be technical. A lot of these calculations come as a result of very complicated partial differential equations, numerical activity and whatnot. I will not be technical, but I will require your attention. So if you are about to fall asleep, I think this is the right time to do it, because otherwise, you know...
thanks for letting us know.
Good. If I miss you in the middle of the way, it won't be helpful. So this is a group of people at AI. There are two flavors, blue and red. All the people in blue are interested in vacuum. All the people in red are interested in non-vacuum, so neutron stars. And then you can see there is a number of people who have contributed to these results. So this is what we know of the kick. And I say now because when I first wrote this slide, the Goddard group and not yet written this result, but now I have adapted this slide in order to take into account this added result. So I've written it in my convention because I have different symbols for the spin and the mass ratio. But essentially, this is what we know as a result of a number of things that are right here. This is quite obscure, but I'd like to guide you through it. So the kick is the result of a broken symmetry. Anytime you break the symmetry in the binary system, you produce a net recoil. And you can produce the asymmetry either in the mass ratio, the difference in the mass ratio, and this is this green contribution here, or you can produce it through an asymmetry in the spin. So this is the spin asymmetry in the equatorial plane. How do you see this? Well, because it's got a perp sign, okay, and you can see this is decomposed in the E1 and E2 vectors, unit vectors, which are the ones in the plane. And then there is another contribution to this velocity, which comes in from the spin asymmetry of the plane. Okay, so if the two black holes are non-spinning, you only get the green. If the spins are orbiting and they're aligned spins, then you get just the purple. If you have something which is instead in the plane, you also have a contribution in the z direction. So the blue is what gives you the super kick, okay? And this is the correction that Cole was mentioning. I'll try to explain how you get to this formula, but this is what we know now. Actually, this is not exactly the formula that Cole has reported in his paper, because there is this additional term, which is a quadratic term that they don't consider, but that I'll show you is there. This is instead what we know of the final spin. Again, it's a formula. And this is the final spin norm. So this is a dimensional spin. It's j over m squared. And as you can see, so this tells you that we can predict the norm and direction, because we can also decompose it into two orthogonal components. once you know what are the initial spins, so A1, A2, and the mass ratio, which is Q, and then you also need, of course, 3 angles, which tell you about the orientation of the initial spin with respect to the orbital angular momentum and among themselves. So alpha, beta, gamma, these 3 cosine angles. And this guy here, the little l, it's the third vector, that's how we name it, and it's essentially a measure of the orbital angular momentum which you have not radiated, and therefore you are giving to the black hole. So what is relevant in terms of this formula is that all of this relies on some assumptions which I will tell you about, but essentially has 5 coefficients. They have this funny name because of historical reasons, but everything is determined in terms of these 5 coefficients, and these can be constrained from numerical data. Okay, so as I said, we have built our understanding starting from something which is a kind of learning ground, and this learning ground are line spinning boundaries, and we try to extract as much of this information as possible, just to make sure again that we are synced in terms of what is it that we're doing. Are we working in vacuum, so there is no matter here, and I'm really concentrating in the last, say, 2 to 10 orbits, okay? So this is not a partial problem, I don't have the partial problem yet, and I'm doing this through the full solution of the Ansatz equations. So the black holes have either equal or unequal masses, they are aligned or they are aligned with the orbital angular momentum in parallel or anti-parallel, and they are said to be quasi-circular orbits. Now, this is very important, okay? We don't have eccentricity, besides the one we introduced by mistake through our truncation method. So the kind of prototype object is this type, but it's not the only one. Let's say that here is where we learn most of our understanding. If you've never seen a binary black hole evolution, here is the opportunity. So we are zooming in into the numerical grid, and those 2 little tiny dots, those are the black holes, and there are 2 tiny vectors which are the spins. I will now rotate the system so that you can see what they look like. The spins are not the same, although you can't tell, but the apparent horizon, those little spheres, they are slightly different because the 2 black holes have different spins. The mesh that you see with different resolution, that's our numerical grid. And I'll show you now what they look like from the bottom. This is just a measure of the curvature if you want. And you can see why it is such a difficult problem, because you have such a rapidly varying field that you want to resolve that. And that's why you have lots of boxes. I will now start the evolution, and you can start seeing that the system orbits, and of course as a result of the orbiting is emitting gravitational waves. I think this is just about a couple of orbits. Then the thing merge into a single horizon, which has a funny shape. It's not a sphere, as you will see, and this is mostly due to the fact that they have different spins. So I will now go around this to show you the shape, funny shape of the apparent horizon. It's not even actually symmetric. And then I will continue the evolution. Okay, so that's the typical parapolar wave emission that one expects. You see the tiny black hole at the center, and now I'll zoom out further out to see what this looks like from the actual computational grid. This is not the outer edge of our computational grid, but just gives you an idea about the science. And what we do essentially is calculate time variations along a certain direction of this grid. Okay, so that was a black hole which has a certain angular momentum, a certain recoil velocity, and everything. Something you can't really see by eye. Okay, so here is how we understand the recoil. I think people have already talked about this, but let me just say something about it. So, unless the speeds are equal and the mass are equal, you always get a kick. And it is because the emission of gravitational waves is beam and it's asymmetrical. So if you think about the black holes as lighthouses, they are emitting gravitational waves with a certain direction, and this, because the 2 are not emitting at the same rate, there's going to be a difference when you look at the same object when you after a pi rotation in the phase. So a simple mechanical analog is offered by this called a rotary sprinkler. You probably have one in your garden. The idea is that if you have water going through this, okay, you will have loss of momentum. And if the thing is perfectly balanced, then it will stay put where you placed it. On the other hand, if one of the aperture has, a defect or something, then there's going to be a different loss of momentum in one direction, and this means that the sprinkler will start to spiral, actually. And as you increase the water flow, the spiral will become larger and larger. So at the end, because there is a net momentum in one direction, and you stop the water, the thing will just, of course, on the grass will stay put, but if it is in vacuum, it will just keep on going. So that's what happens with black holes, pretty much. If you try to see the kick in the actual numerical simulation, you can't. You won't see a black hole moving in the grid, quite differently from what you see in these SPA calculations. So all you can see is through the waves, and it's even difficult to see it from the waves. So here is a way which we have devised in order to see this. This is Psi4, if you want to use a measure of the gravitational wave content, projected onto a sphere. We're looking on top of the sphere, and now we're going to see any non-m equal 0, so anything which is not actually symmetric, or m equal 2, a symmetry. That is a signature of the fact that you have a net momentum in one direction. So you don't see, this is pretty much an m equal 2 like a bar, but then you would see that the bar has a more pronounced shape in one direction. I don't know if you've seen that, but that was the kick. So as I said, it's a very tiny effect that yet has a lot of astrophysical implications. Okay. Because you are sensitive to asymmetries, it's clear that the kick is essentially produced in the very final stages. That is really in the almost final part of the last orbit. Okay? Here I show you a trajectory of a barring black hole. So it's two, but I show you just one. So the black hole starts here, then it inspires there's 3 orbits. And then you see that this last portion, the one which is in the red dash, that's when the kick really develops. Now I'll show you the time evolution, evolution of the velocity of the components of the kick. Okay? So this is a time 300m. You see, essentially the velocity is always 0, very close to be 0. And it's just at the very end that the kick velocity goes up to about, 60, 70 kilometers. And that's why the kick is really built in the last portion of the orbit. And it's not a trivial piece of physics and relativity to understand how this is actually produced. And I don't think we have a clear picture yet. It's obvious, the only thing which is obvious, that the thing is produced at the very end, and there is a subtle balance between the multipolar components of the radiation which interfere, and produce a kick in a certain direction. But if you want, this is pretty much the phenomenology. Okay, now let's try to do some more physics. That's how we started calculating things. We said, well, let's suppose we take a black hole and we keep it with a given spin, say 0.58, and then we take another black hole and then we change the size of the spin of the other black hole, so that we go from this configuration here, which is R0, in which they have anti-parallel spin, to this one, which they are parallel and equal. And of course you go through 0. Now, from what I said, it's obvious that this is a symmetric system. So you don't expect to see any recoil velocity from this. And this is the one you expect to see the largest, and of course it is in all in between. This is shown in this diagram, where you see time, and you see that this object R0 tends to merge sooner than this one, which is not R8. R8 will be 0 all the time, and that's what it actually is. And then you see that all of this have, as you have a more symmetric system, the thing takes more to merge. It is called these hang up. Okay, they tend to repel each other, and also the spin goes down. Okay, so when you have something like this, and I'm here showing just the same measure using 2 different methods, what you can think at this point is, all right, let's try to look at the final value of the velocity and plot it in terms of this parameter with our order clock. That's what you get. Okay, so this is the spin ratio, and this is the final velocity. And this instance just shows that if you don't do things properly, you don't see an important behavior. So at this point we can say, well, let's just compare with what we know from post-Newtonian theory. So post-Newtonian theory essentially gives you this formula here. The first one is the mass asymmetry contribution. Because we're using equal mass, Q is equal to 1, and so this term doesn't really matter. The second part, you see, it's quadratic in this term A1 over A2. So the post-Newtonian prediction is that this should be a straight line. And that's what we thought it was. But then, as our precision increased, we actually realized that this is not quite a straight line, that you add a quadratic behavior, which fits the data much better. Okay? And as I'll show later, this is this contribution. Okay. Now we want to model this. Okay, so if you want, this is just phenomenology. You can think of doing zillions of numerical simulations, and every time you get something of that type. But on the other hand, what we would like to do is get something which is an efficient way of describing the system without having to actually do a numerical simulation. So what we would like to think is binary black holes as an engine, where you put in as input 2 black holes and you get as an output a single black hole. And the name of the game is knowing all about the final black hole in terms of recoil, spin, and whatever. So the space of parameter in general is 7-dimensional because you have 3 components of the first spin, 3 components of the second spin, and then the mass ratio. But as I said, we started something which is simpler, so we have equal masses and just aligned configuration. So the spin is just along the z direction, and we call this for simplicity A1 and A2. You can say if you are in vacuum, this is just one of your choices. If you are in non-vacuum, then there are arguments coming both from observations, and I mean the super kick and so on, but also been discussed by Tamara and Cole, to believe that it's not just any configuration, it's probably a preferred configuration in nature. Okay, so at this point we can start doing a statistical approach. And we introduce this concept of a spin diagram. So suppose that you want to fill this diagram where you have the spin of the first black hole and the spin of the second black hole, and you want to populate it with initial data and evolve them and see what happens. So we have created these sequences. And what is this interesting? Well, it is interesting because you have a compact support, all your parameters go between -1 and 1. You have obvious symmetries that you can exploit. In other words, it doesn't matter which one is 1 and which one is 2, so you can really swap this upper triangle with a lower triangle. And because at the end you end up with something which is a scalar, you can easily do least square fits. Okay? So in this way we can build information about the final black hole in terms of analytic functions. So you have to start somewhere, and you just say, well, I say that my kick velocity is just a second-order polynomial function in the 2 parameters, A1 and A2, and I have this set of coefficients. Okay, this is certainly allowed, but then you're not really using all your knowledge. Okay, there is some knowledge that we have, and for instance, we have the knowledge that, as I said, you can swap the 2 black holes and get the same answer. So this condition is an equation that you can impose. But you also know that if they are the same, they don't give you any recoil velocity. When you do this, you kill 4 of the 6 coefficients. You know them analytically, and as a result, so this is telling you that C0 is 0, D0 is 0, and there is this sign change in C1 and D1. And this means that you have now a much more compact expression, which is just of 2 coefficients. You see there is this coefficient 1, which is the linear term, and there is this other coefficient, which is the quadratic term. This is what it looks like when you see it in 3D. So this is the actual fitting function, and the data are the ones indicated with a star. You can see the function is quite simple to describe, and in fact, its lower polynomial already captures most of it. And you can also see this in terms of contour plots, okay? And so let's study this a second. An aligned configuration starts in this quadrant here, okay? Because you have A1 has to be the same sign as A2, product has to be positive. And that's where the 200 roughly kilometer comes, I think, from Tamara's talk. On the other hand, if you work in this direction, say the northwest diagonal, then you can get onto this very steep curve here, and you can get much higher. That's why you get the 450 kilometers I was talking about the first day. Okay? So, in principle, you can use this in your own body simulations if all of your black holes happen to be aligned. And yeah, so this is the maximum velocity I was referring to. So just to recap, what is nice about this formula is that it gives you an improvement over the linear PN predictions, tells you there is no recoil for symmetric systems, that the maximum recoil R for A1 equal minus A2, and there is a linear scaling along the diagonal. So this is probably not quite clear, but when you are along this sequence here, you are linear because this term cancels out, and so you really have just a linear growth in this direction. So it's quadratic, but in general, but it's linear in this direction. And this also explains why other groups have recorded a linear growth, because they were looking at that in this direction. So, as I said, agreement without numerical signs. Now, this is just a portion, okay? This formula is just a portion. This is the portion of the recoil velocity which is due to alignment, the aligned part of the velocity. Okay, so here I'm assuming that the masses are the same and that I don't have spins in the equatorial plane. The formula that I showed you at the beginning, the first page, that is a more general formula. Okay, but right now I think we understand this with a certain confidence. All right, then what you do is you do exactly the same in logic, also to model the final spin. So we define J, A as J over M squared, A final, and then you say, well, let's just model it as a quadratic function again. And again, you impose conditions like you can swap the black holes, and that, and then there's this other condition here that if the two black holes have the same spin but they are opposite, then this quantity has to give you a constant. This is coming from the fact that we know that if this is the same constant when we have non-spinning black holes. So this is, if you want, a piece of interesting evidence which doesn't derive from first principle, but all simulations tell you that if you have non-spinning black holes, you produce a spinning black hole of a given spin. And then if you do the same with spinning black holes which have equal spin but they are anti-parallel, you get exactly the same black hole. It is as if spinning and equal spinning black holes behave as non-spinning black holes. Okay? Well, then you end up constraining the coefficients and you have an expression of this type. So you have this term, and you see that if you look at the coefficient, this is the most important one, this is the 0.68, 0.69, this is what you obtain in the case of a non-spinning black hole. Then you have a linear term and a quadratic term. And the quadratic term is extremely small, but it's there. This is what the actual three-dimensional distribution is. Again, these are the two spins. So you see that the final spin increases along the southwest, northeast diagonal, so along here. You have the maximum spin, which is 0.96, and a minimum spin of 0.35. Okay, you shouldn't take this as a very accurate number. I mean, this is just the precision of the actual numerics, but there is a certain systematic error which is much harder to measure. What is interesting that Damour in 2001 had predicted that there was a maximum spin, and as you can see from this curve, there is no evidence there is a maximum spin. These are just numbers. Okay. Now we go into a different direction of the space of parameters. We consider unequal mass but equal spin binaries. Okay? Again, still talking about just two dimensions is easier if you want to do things. So, so far I consider A1 different by A2, but the two masses being the same. Now I consider A1 equal A2, but the masses being different. Okay? And in particular, I introduce this parameter nu, which is this symmetric mass ratio. And nu goes between 1/4 and 0. Okay, now I have I see that in order to get something which is more accurate, I need to use a cubic dependence. Okay, I have two parameters a and u, and I do a third order polynomial. And you see I have all of these coefficients because I have mixed terms like a squared nu or a u squared and so on. But once again, rather than fitting my whatever 10 coefficients, I use some physical considerations. I know that in the extreme mass ratio limit, whatever is the initial spin, or one of the black hole, I have to end up with the same black hole. So A final has to be equal to the A, okay? And this already gives me 3 coefficients that set 1 equal to 1. And so, by using this, I reduce this formula to just this expression here. And you have 6 coefficients now. And I can use another condition coming from the extreme mass ratio limit to contain one further condition, one further coefficient. So this gives you, I think, is the best way of appreciating that the physics is very elementary. Here I'm showing the spin, okay, of the system and the symmetric mass ratio. So along this direction, 0.25, I have equal masses. And here I have the extreme mass ratio limit. I have a very big black hole and a tiny black hole. And of course, in this case, I just have a straight line. Okay? These are the conditions I need to know. And all of these squares, this is just numerical data. So that's the condition I have to satisfy. And it doesn't surprise you that it's easy to find a function, a lower order polynomial that fits everything quite nicely. So the dash is actually the analytic function. So then you can check, well, is this really accurate? Okay, so this is the actual comparison against the numerical data. So the dash line is a 2D fit, and you see all the dots are the numerical data. These are the residuals. You see the residuals are all very small. This is another approach, BKL, Bonanno, Kidder, and Lehner, in which they exploit point particle analogies. It's a very useful tool, but it's not always a very accurate measure. So this is the equal mass. Essentially, this is. Sorry. I first showed the data in this direction, then I showed the data in this direction. This is instead the non-spinning, okay? And then you see that also in this case, a single fit captures most of the important information. This is the 0.69 I was mentioning about. Okay? Once again, the residual are extremely small. Now, because you have an analytic formula, then you can start asking yourself interesting questions like, if I have 2 spinning black holes, can I ever produce a Schwarzschild black hole out of them? It's a trivial question. All you have to do is in your equation set the right-hand side to be 0. So graphically, you take this curve and you have to intersect with the zero, at the 0 plane. And you get this type of curve. And then you ask yourself, no, that can't be right. I should check this. And what you do is you run a simulation. That's where you expect that condition there to be verified. And then you do a simulation, and you find out that black hole you produced, although you were starting from very rapidly spinning, minus 0.8, you end up with something which is 10 to the minus 3 away from the Schwarzschild. How does this happen? Well, it's very simple. The angular momentum is like that, the spins are like that, you put them together, vectors, you get 0. It's not quite like that because you also have angular momentum being lost, but that's essentially what it does. What is interesting to know is that you never go to 0.25 here. Okay? This means essentially that you really need unequal masses and anti-aligned to the orbital angular momentum in order to do this trick. Otherwise, it's not so good. This also tells you that if you find an isolated Schwarzschild black hole, then that's very likely to be the result of a merger rather than the result of a stellar evolution. Okay, so then you can ask other questions. Do you spin down or do you spin up in general in case of aligned binaries? Again, you just have to consider when is it that the final is equal to the initial, and this is just a line in this plot. So this is the possible space, and you see that the only situation in which you can have a spin down is in this region here. Okay, so most of the time you tend to produce a spin up. And this is quite obvious. I mean, you can think, if you start from Schwarzschild black hole, you produce something which is already a curved black hole. So in general, the process leads to a spin up. Okay, so clearly the merger, I'm really concentrating on the merger of a line black hole statistically leads to a spin up. Okay, and this could be used, in fact, has been used in a recent paper by Berti and Volontaire to understand the impact on cosmological evolutions. The bottom line is that the merger plays a very little contribution in this story, but nevertheless it's a contribution. Now, a consistency check. Because as I said, we have done a fit in two different directions in the space of parameters, and we have come up with two sets of coefficients. But then these two sets of parameters merge in one line. Okay? So we can require, we must require, that the spin obtaining equal mass and equal spins is obtaining the spin in an equal mass, equal spin formula when you impose that there are equal masses and there are equal spins. So you end up with some algebraic relations among the coefficients. Okay? So just to make sure, in one case I was defining these coefficients P0, P1, and P2, and in the other one I was using T2, T3, S5, S4, and P0. If they are telling me about the same modeling, then these should be identities. And as a matter of fact, these are identities within the error bars. Okay? Each of these coefficients has an error. Okay, just to recap, because now comes the kind of the leap into the most complicated structure. We have equal mass, unequal but aligned spins, unequal mass, equal but aligned spins. We found that they match exactly in the intersection. Now we can extend, in the case of equal spins, replace A with this expression here, and we can model A final as a function of the mass ratio and of the two spins as long as they are aligned. So this is the general expression in case they are aligned, but it's just 3 dimensions out of the 7. Can we cover also the 4? And the answer is, of course, yes. And this is something that Enrico Barros and I worked recently. So the idea is that on the basis of this knowledge, you can tell now what is the final spin of a generic binary. In order to do this, we have to make some assumptions, which we think are reasonable, and I'll tell you them now. Some related work has been done already by using Blackford and by this Bonanno, Kidder, and Lehner. So the first one is that, for simplicity, in order not to have another parameter in our expressions, we say that the radiated mass is very small. And actually this is quite true. I mean, usually you see that the amount of mass loss of gravitational waves is a few percent. Okay? Then we say that the final spin is equal to the sum of 3 vectors, the 2 initial spins plus this other vector L tilde. Now, this is the 3rd vector, the one I refer to as the 3rd vector. If you just rewrite this in terms of angular momentum conservation, at the end you have the final spin plus what you've lost, and at the beginning you have the 2 spins plus the angular momentum, the orbital angular momentum. So L tilde is nothing else but the difference between the orbital angular momentum and all the radiating part. Okay? So essentially, L is what you cannot lose. Okay? The third assumption is that L tilde is parallel to L. Okay? This is telling you that, you know, in the billions of years in which you emit gravitational waves, the system is almost planar, and so all the gravitational waves, all the angular momentum you lose is along the orbital angular momentum. Now, there are some situations, like for instance when the spins are parallel to L, or when they are 0, or when they are opposite and they are equal mass, in which this condition is actually exact. But it's not true in general. Okay? In general, one expects the radiation angular momentum as a component parallel and perpendicular. But also one expects that the L is larger than the perpendicular one. So this is clearly a way in which this can be improved in estimating what is J-rod per. And then there's a 4th assumption, which again is the one I was telling you about. It's kind of coming out of the numerical relativity. If you have equal mass and anti-parallel spins, the system really behaves as if the spins are 0. Okay, so steady difference, equal mass binaries with equal and opposite spins behave as non-spinning binaries. All the simulations to date show that this is true. So if there is a deviation from this assumption, it has to be at a very high level. Okay, now with this assumption, it's easy to model the third vector, okay? And we can provide a unique expression. So you can write the modules of A in terms of the three spins, of the two spins, A1 and A2, the cross product, the cos alpha, plus the two cross product with L, so A1L and A2L, plus the normal L. Alpha, beta, and gamma is 3m, so you can think that L is this vector, and then you have beta and gamma, and then you also have alpha between S1 and S2. That's all it takes. Then you can just compare this with your data, and you end up with this fitting expression for L. And you can see that everything is determined in terms of the spins, of the mass ratio, and of the fitting coefficients. Okay? So you have just 5 fitting coefficients, which tell you all you need to know about this third vector. So the question is, does this work? It sounds like a complicated construction, and I'll show you that it actually works, at least to the best of our knowledge. So this is all the aligned binaries that we know. So we're hitting, almost 100 here. So this is all the published available data. So these are either equal mass, aligned parallel spin, or equal mass anti-parallel spin, or parallel spin but unequal mass. And you can see that these are the residuals. So this is the difference between what you get from the fit and what you get from the numerics times 100. You are below 2%. I should also say that this is collecting all the data from different groups, and different groups have different encodes and different truncation errors, different systematic errors. So it's amazing, at least to me, that yet, although we're really collecting, it's like collecting data from, I don't know, 4 or 5 satellites and seeing that they are close to each other to a few percent. But that was the easy part. So our line, essentially, we know all about it. This is the much tougher, test. So these are the misaligned boundaries. You see, we have less data here. And again, the symbols are the published results, and the star is the result of the fit. Okay? And plotted here, we said, are just the residuals. Again, in this case, the residuals are a bit larger, but it's again on the order of a few percent. For some cases like these ones, we don't really have the final spin. This produces a vector, final vector, which is not along a coordinate axis, and so we just have the parallel component. But we can decompose it again, and we get a very good match to that. Okay, so the residual is slightly larger, but still a couple of percent. And this is the most difficult comparison. Calculating the difference with the actual angle. So you can actually calculate what is the final angle, this theta. Now this is, I should say, this is a very complicated measure, and there's just one group besides ours that has managed to calculate this angle. So this is the one at Rochester, and you see here the error is much larger. Okay, you have an error of a few degrees in some cases. But I think it's still unclear how to make this measurement. And these measurements should not, the actual error bars are not the one of the systematic error. And so this argument doesn't surprise me too much. I think there is more to understand in this respect. I will not show you how you can improve this, so we'll go straight to the summary. Numerical simulations have made huge progress in the last couple of years, okay? And we have very high precision measurements of the evolution of generic without reason binaries. I say without reason because we still don't know how to do very high speed ones. It's interesting that numerical activity is no longer just looking like a branch of applied mathematics or computational physics. It's actually doing some input to astrophysics in terms of recoil and spin, and data analysis, computational data analysis, building templates, arbitrary code, and so on. The modeling of the kick has shown that some very large ones are possible, at least in principle, but a complete and accurate expression, in my view, is still lucky. something which I haven't mentioned is that that formula that I've shown on the first page, that has been built using very special configurations in which the speeds are either in the plane or out of the plane and parallel to the orbital angular momentum. When you have these aligned binaries, people who have done this calculation find differences of 100 km per second in their estimates. So I think it's a very delicate issue, and I think we don't master it completely. The model, the final spin on the other hand seems to be much into a better control, and we have an expression which has precision of a few percent for generic configurations. I think both expressions will be improved in the future, but as far as my understanding goes, I think they are pretty good already to start doing some interesting astrophysics and cosmology. We have about